658, lecture 31. Yesterday we were talking about D2A conversion and specifically the spectral properties of a D2A converter. We said that a D2A converter is a device which takes a discrete time signal and converts it into something which is continuous in time. So it takes a train of discrete time impulses and converts it into a train of continuous time impulses. And there are practical problems associated with trying to generate a Dirac delta train with whose areas are proportional to the digital input code. And not only that, it's a waste because a lot of the energy is in the images, which you don't want anyway. So a saner strategy is to use not a sharp pulse like a Dirac delta pulse, but something with a lesser amount of discontinuity, which is equivalent to saying that the high frequency content of that signal is small to begin with. So two candidates were identified. One was the NRZ pulse, which kind of say looks like this. Another alternate shape is the return to zero pulse shape. Just to build a little more intuition, a DAC with an NRZ pulse shape will produce, for example, if this was the discrete time signal, an NRZ DAC will produce an output as shown in red here. And what do you think a return to zero DAC will produce? It will produce something twice the height and half the width, come back to zero, go twice the height, half the width, so you can see that the pulse, the DAC output waveform is returning to zero during every bit period. Can you comment on the low frequency content of both these signals? Both of the same low frequency content. Why? One way of looking at it is the area under the pulse in both cases of the impulse response is the same in both cases, which is equivalent to saying the area under the pulse is nothing but is a DC gain, right? So the DC gain is the same in both cases, and anyway, in yesterday's class we said that this is AT sync FT. The amplitude is twice in that case, but the time width is half. So the gain at DC for both these things are the same. So the only difference is in the NRZ pulse has got a notch at the sync will give you a notch at 1 over T and its multiples. Whereas for the return to zero DAC, the sync will give you notches at 2 by T and its multiples. So the first image at 1 over T is not definitely as attenuated as it is in the non-return to zero case. Then the obvious question that was raised towards the end of last class was, if we know that the NRZ seems like an obviously better choice, why bother studying about return to zero at all? Okay, so it has to do with practical implementation. So we have this NRZ pulse shape. So in other words, we want to have a filter whose impulse response is this. So how will you implement it? You think you'll be able to get? Do you think you want to put an analog filter with this kind of impulse response or what? First of all, is an impulse response like this realizable? To get an analog filter of this form is impossible because there are sharp edges. What we want to do is not to take an impulse train DAC and explicitly put a you certainly do not want to do the following. You do not want to generate an impulsive DAC, put a filter like this, with an impulse response like this, which is not realizable anyway. Okay. The simplest thing to do is do what was suggested by one of these chaps. Let's say you've already seen an example of a DAC, and where is that? That's in the resistor string of the flash. A resistor string of the flash is basically nothing but a DAC in disguise, because if this was the top of the ladder and this was the bottom of the ladder, these are all equal resistors. These were generating equally spaced voltages. If you want an analog output which corresponds to a digital code D, one simple way of doing it is just simply have some digital logic which will switch one of these guys to the output. Cheapest way you can think of making a DAC, right? And you can see that nothing special has to be done to realize this hold function, correct? So as long as this is held, this logic, these switches, the position of these switches inside the mux is held for one complete clock period, automatically the analog output voltage will be held for a whole clock period. That will give you the NRZ pulse shape without any hassle at all. In fact, to do a return to zero, you actually struggle, because after half the clock, you have to switch to zero. You understand? So generating the return to zero clock pulse is not quite as simple as, it's not complicated, but it's not, definitely not as straightforward as simply doing the NRZ. The bottom line is basically that while we analyze the whole system, assuming a filter with impulse response, taking a Dirac delta train and then putting a filter with the sync type impulse response, frequency response, definitely that's not how it's going to be. That's what you use to analyze, but that's not what you use to implement. Is that clear? Now the question becomes even more critical to answer is, then why bother about the return to zero at all? In fact, it turns out the return to zero is actually not unpopular. It is actually quite popular in a lot of applications. So the question is, if it's got so many problems, why is this popular? There must be something in the return to zero which is not there in the non-return to zero. Okay, and as I said, it's got to do with implementation. See, whenever in an ideal NRZ output waveform is supposed to be like this, I'm going to just grossly exaggerate the time interval as well as. So this is an ideal DAC output waveform. So what can you say about these edges? In an ideal NRZ waveform, they must be infinitely sharp. In practice, what can you say about these edges? So finally some transistor is charging up some, some node, the node has got parasitic capacitance, so clearly no voltage can just jump up just like that. It must things take time to happen, right? So in practice what happens is the output does probably something like this. Again, in practice you will find that the rise time need not necessarily be equal to the fall time. Okay, so rise time in general, while you can definitely design things to be the same, it will turn out that the rise time will not be equal to the fall time. Can you explain why rise time need not be equal to the fall time? Typically, if you want to pull a waveform up, what do? Current is being pushed in. So, for example, a simple example of a 1-bit DAC. What is a 1-bit DAC? There are only 2 levels, correct? An example of a simple example of a 1-bit DAC is a CMOS inverter output waveform. Okay, it is either VDD or ground. Okay, the rise time is basically dependent on the NMOS transistor. How fast you pull it up is dependent on the PMOS transistor. How quickly you can pull it down is determined by the NMOS transistor, and you've done all this stuff in courses where you got to make the PMOS transistor bigger than the NMOS transistor to get rise and fall times, and even then you know that this you can only make them approximately equal, you cannot make them exactly the same. Okay, so the same thing will hold also. I mean, you can even though you may not be able to see it at this point in time, it's conceivable that if you make a better a DAC with larger number of levels too, that might hold in general. So by design you can probably make the two of them the same, but in practice there will always be some finite difference. Let's see what happens when I put a sequence. Let's take a 2-bit example. So if I had a sequence 1 1 1 0 0 0 as the input sequence to a 1-bit DAC, what do you think will happen? It's like this. It goes up, stays 1, and then stays 1 again, and then falls off. And please note that I am grossly exaggerating the rise and fall time differences just to bring out this point. Okay, 0 0 0. And let's say this is periodic, so again what happens is it goes up 1 1 1 0 0 0. Okay, let me now plot a sequence, the output which you would get if you had the following sequence 1 0 1 0 1 0. Okay, so how do you think this waveform will look like? 0, it jumps up, then starts to jump down, what happens here? Again goes up, comes down. So this is 1, this is 0, this is 1, this is 0, this is so finally you want the DAC to be a linear system, right? So the output voltage must be, what is a linear system? If I put in whatever a waveform some x1, I must get an output equal to, the input was x1, the output was y1, and if the input was x2, the output is y2. If I put x1 plus x2, I must get y1 plus y2. That's what a linear system should do. Let's figure out if this is a linear system. Specifically, look at these two waveforms, these two periodic waveforms. What can you say about the average value of both the sequences? This is the average value of both these sequences is supposed to be half. In other words, the average value of both the input digital sequences is the same. So if the DAC was linear, then what would you expect the average values of both the output waveforms to be? They should be the same. Okay, if the DAC is linear. Alright. Now let's see what the average value of this waveform is. What is the average value? Let me call the area of this triangle A1 and the area of this triangle A2. So what is the average value now? If A1 and A2 are both 0, then what would be the average value? It would be half. So if I took an ideal waveform with 0 transition time, then all that I need to do is add A1 and subtract A2, correct, to an ideal waveform to get the real waveform. Okay. So the average value of this thing is simply add A2 and subtract A1. Is that what? Yeah, it is. That's what it should be. Right. So it is, average value is half, which is what the average value would be of the ideal waveform. Okay, then I should subtract A1 and add A2 and divide by 6. Is this clear? Why is the 6 coming? And that's the period of the. What is the average value of this guy here? Half plus A2 minus A1 by. So now can you comment on whether it's a linear system or not? If the average value of the input waveform is the same in both cases, the average value of the output waveform should be the same in both cases if the system was linear, right? That's definitely not happening. Another way of doing it is if I subtracted the two waveforms, right, the average value should be 0, correct? That also doesn't happen. So clearly this is a nonlinear thing. So when does this nonlinearity go away? Of course, when A1 equal to A2 is 0, then there is no problem. Okay, I mean that's, you know, that's not practical anyway. Another thing that will still make things look linear is when the rise and the fall time are the same. Okay, so which is also in practice in a lot of times it's not possible to achieve exactly. You can kind of make them identical, largely identical, but the exact and here I have taken a very simple case where the rise is just happening at a constant slope. In practice the slope will also obviously not be a constant. Okay, so this rise time fall time asymmetry causes distortion in an NRZ DAC. Let's see what happens quickly when you have a return to 0 DAC. So this is what you would get for an RZ DAC. Can you comment about the average in both cases? It is not what you thought it should be. Okay, ideally if the edges were sharp, but in both cases it is and that still doesn't mean it's linear. Alright, but you can clearly see that given whatever sequence it is, you can write it as sigma k even with finite rise and fall time. You can always write the output of a return to 0 DAC as summation over k p of t minus kt. Alright, it's just that with finite rise and fall time, the pulse shape which should have been like this, okay, will actually become, say, something like this. But you can still see that the output sequence can be written like this, some Bk times B is the digital, is the value of the code times P of t minus kt. So all that the finite rise and fall time as well as any asymmetry between them will do, in other words, it just changes instead of being a sink which goes down at, instead of being the frequency response, instead of being sink 2ft, it will be something else. Okay, but that's just a change in the transfer function. It is not a nonlinear phenomenon. You understand? So this problem with rise time fall time asymmetry is often in the literature called the ISI problem in DACs. And the ISI stands for inter-symbol interference. So this is why, even though return to zero DACs have a lot of other issues, they are still popular in applications which demand extremely low distortion. In principle, ideally, when you put in a sine wave, okay, you must get a sine wave at the output. Isn't it? I mean, to within quantization noise, if you put in a sine wave, you must get a sine wave, correct? If there is do you agree that this is a nonlinear phenomenon? Okay. Now, in practice, because it's nonlinear, if you put in a sine wave, what this means is that you will not get, even though you put in a discrete time sine wave at the input, okay, with let's assume that the DAC has got enough resolution so that the quantization noise is very, very small, okay. So when you put in a sine wave, you expect a sine wave at the output, right? But if there is nonlinearity, what will you get? You will get sine wave and its harmonics, correct? Simply because this is nonlinear, okay. So that is the reason where, so in applications where you, especially in communication applications where distortion is important, you will find that a lot of these DACs are actually return to zero DACs, okay. I mean, in a lot of these communication applications, distortion actually turns out to be quite important, simply because, see, you know that you're going to eventually modulate your whatever information bearing signal you have to a carrier, right? And service companies providing you mobile service make money only when they are able to maximize the number of users, right? Which basically means that you just can't waste spectrum. I mean, if you're actually supposed to transmit stuff within this band, okay, all right, and to maximize the number of users, your neighbor is basically sitting at is doing this, okay. This is okay. Now, if he is distorting, right? If there's a lot of nonlinearity in all his transmission, what will happen is that his spectrum will spill into neighboring channels, okay, which means that looks like noise to you, because you don't really want to listen to what he's saying, right? Okay. And the way information is transmitted nowadays, I guess all of you know this, you must have done this in analog and digital signal processing. You basically have the in-phase signal, the quadrature signal, right? And then you have, in the simplest case, cos omega ct, and then you have sin omega ct, and then you add these two, and then you go into a power amplifier, and then this is the transmit antenna, okay. And the I and Q, I mean, depending on what kind of digital modulation scheme you have, you don't directly put the bits out into, you don't modulate up the bits directly onto the carrier. The reason why you don't do that is if you take the bit stream and modulate it, the bit stream has got so many sharp edges, right? Sharp edges basically means high frequency content. So when you translate that high frequency content up to the carrier, it will basically spread all over the place. You understand? So, so what you do is you want to make sure that these waveforms have sufficiently smoothly controlled slopes so that you manage the spectrum, the spectral width properly. Okay, I mean, that's all this BPSK, QPSK, all this other stuff with this raised cosine pulse shape and all that is doing, what they're all doing is managing the spectral shape. Okay, and all that is done mostly done digitally, and you have, in most cases, you have a D2A converter driving the I, a D2A converter driving the Q, alright, and you can't afford to, even an NRZ pulse shape, I mean, if there are images in the I and Q paths, when you translate them up, then you're just moving the frequency content up in frequency. If there are a lot of images in baseband, they will all, show up at the carrier also. So what you do is, you don't want to do that. What you do is, this is the data corresponding to the I, okay, this is the DAC, then you must put a smoothing filter, alright, and similarly the DAC smoothing filter, and then you modulate it up, and so this is I, this is Q, okay. Then you modulate it up and you're all set. So especially in applications like this, if the DAC has got nonlinearity, what it means is that there will be, things will start spreading, okay, and that's something that you don't want. So in a lot of these communication type DACs, you will find that the return to zero pulse shape is used, okay. Of course, the filter has to be stronger for when you put the smoothing filter has to do a better job when you have a return to zero pulse shape, because the jumps in the input are much larger. But a lot of times it's worth it because you can avoid the distortion problem altogether. Okay, and you can think of any number of examples where distortion is equally important. Another example that you will have more and more occasion to get familiar with, I guess, in your professional careers is this what is called direct digital frequency synthesis. Okay, so if you want to make a sine wave at I don't know, some arbitrary frequency, one thing is to build an oscillator and make sure that you filter off all its harmonics. Another way, which is gaining a lot of popularity these days, okay, is simply what is called direct digital frequency synthesis, and that is you have a ROM. The advantage is most of the processing can be done digitally. You have a ROM, and this goes and drives a high resolution DAC, okay, and then you put some kind of filter, and this is the output. And if you want to change the frequency, it's just basically the rate at which you read stuff off the ROM, okay. All right. So this is so you can so this is called direct digital frequency synthesis, and gives you the opportunity to switch frequency on the fly without having to wait for oscillators to change the frequency of oscillation and all that, which takes a long time. This will give you instantaneous frequency hopping, okay. So a lot of communication standards have what is called, there's something called frequency hop spread spectrum, okay, where you keep changing the carrier at which you transmit, and it typically becomes very difficult to have a local oscillator which also follows that hops as quickly, okay. A good solution in that case is this system, and today a lot of these function generators also exploit this principle, okay. So because everything is quite modular and it's all digital, this can be done in an FPGA type stuff, and then you just buy one good DAC and you're all set, okay. And today you can get, for example, if you go to the Analog Devices website, you will see that they will sell you a 14 or 15-bit DAC running at more than 1.5 gigasamples per second, okay. So once you have that kind of thing, it's actually you can design, in principle you can build a sine wave source whose frequency is programmable all the way from 0 to about fs by 2, okay, by simply using one DAC, and the precision of the sine wave you get will be, since you have a 14-bit DAC, will be guaranteed to be about at least 80 to 90 dB. A 14-bit DAC ideally should give you signal to quantization noise ratio of about 86 dB, okay. So in practice you will not get that kind of thing. You probably get maybe 75, depending on the quality of the DAC, okay, 70 to 75 dB. So in other words, you can get at least a sine wave with 10-bit precision over the entire 0 to fs by typically to between 0 to fs by 3 or fs by 4, that kind of thing, definitely before you, without any major hardware, right? All the hard work has been done in the DAC, okay. You buy the DAC, you get some ROM and then glue the two together on a board and you're all set. So So a lot of frequency synthesizers generators today, function generators of the type you see in the lab, right? There's no more turning the knob. Okay, it's I mean it can all be digitally controlled, and you can get very precise frequency and all this other stuff, because everything is done digitally, apart from the DAC, of course. So here also obviously distortion is a big concern, and so you want the DAC to be linear. Alright, so let's look at the various ways you can conceive of doing a DAC. One is what we've already seen. This is a mux, this is the digital control, this is the analog out. Okay, the mux is simply a decoder which figures out which of these taps must be connected to the output. Okay, so this is often what is called a resistor string DAC for obvious reasons. What are all the problems you can think of? Okay, so one problem is that the output impedance of this DAC is not 0. So one fix for that problem is to put a buffer like this. That solves that problem. Yes. What else? What next? What do you think the DNL and INL of this DAC depend on? So matching of the resistors determines DNL and INL, and it turns out that the matching of on-chip resistors is typically, if you make two identical resistors on the chip, typical matching you can expect between the two is about maybe 8 bits. So 8 bits is like 1 in 256, okay, which is about 0.4% or so, 0.2% or so. So typically, first of all, the DNL INL isn't definitely not better than 8 bits. And please note that all this mux will have switches and all this stuff. So there's basically parasitic capacitances internal to the mux and at all these nodes. Okay. So can you comment on the rate at which these parasitic capacitances get charged as a function of the digital code? If you were trying to tap off this voltage, can you comment on the output impedance here versus the output impedance somewhere in the middle? Here it will be much lower because it is this parallel all this guy. Okay, so this impedance is approximately R, whereas here it will be NR by 2. Okay, so the Thevenin impedance of the DAC depends on the code. Okay, which means that the time it takes to charge up these capacitors, these parasitic capacitors, also depends on the code. So in other words, the pole of the DAC, okay, depends on the code. So is this a linear thing or a non-linear thing? It's a non-linear thing. Okay, so this is a problem also. The next thing is to comment about the mux. Any comments on the mux? How do you think you will be able to do the mux? I mean, there are several ways of doing the mux. Okay, one way is to convert the binary code, and not a thermometer code, but to a 1 of n code. I mean, so you generate this string of 2 to the n numbers, of which only 1 is 1. Okay, and use that to go and control 2 to the n switches. Okay, in other words, you have this guy like this. So this is this chap. This is a resistor string, and each one of these guys has got a switch. This is your mux, okay, and the digital word goes and controls. So there are 2 to the n. The advantage with this is this the only way to do the mux? You can use a tree, right? So you select either the bottom half or the top half, and then then the bottom half, the top half of those sections, and so on. So this can be a tree type mux. So that will basically simplify the the decoding here is actually a pretty complex process because you need for example, if you're trying to build an 8-bit DAC, okay, so you need take 8 lines and generate 256 output lines, and one of these 256 output lines goes to, each one of those switches. So you can see that it's a pretty massive affair. An easier way would be to divide and conquer, right? So you have 8 stages of, divide by 2 type stuff. So you have a tree type mux. Okay. So there the decoding logic is simple. Okay. However, what is the problem there? The switch impedance, switch resistance. There are now there will be 8 switches in the path. Okay. And each one of those parasitic capacitances will have been when you change code, some of those parasitic capacitances have to be moved from what they were earlier to something else and all this other stuff. Okay, so clearly switch resistance is a bigger problem in the other case where you have a tree structure mux. Alright. So in either case, basically you can see that there's a trade-off between the way you realize the mux. So that is another issue. Okay, so typically resistor string DACs are not very popular, except in cases where you want very crude DACs. Let's say you want 6-bit DAC, okay, which is what you used in a flash, right? If you're trying to build a 6-bit flash, the resistor string is nothing but a DAC. Okay, you understand? So unless resolutions you need are very small, typically it's not used. Another way of laying out the resistor string is to do the lay it out as a matrix. Okay. If you have an n-bit DAC, you need to tap off one of these voltages. Okay. A nicer way of implementing it, if the number of bits becomes large, instead of having it run like a string, you can have it run like an array. Okay. And this is very similar to what you do with accessing memory in a RAM, right? So you have a row decoder, a column decoder, and so half the bits will come here, the other half bits will come here, and the decoder complexity is reduced quite a bit when compared to having a dumb decoder which takes the 8-bit word and generates everything.